What you're looking at is one of the most analysed pieces of video in modern history. Captured by US Navy pilots in 2004, it shows a small, white, tic-tac-shaped object moving in ways that defy known aerodynamics. No wings, no exhaust, and no visible means of propulsion. Multiple trained aircrew recorded it using radar, infrared, and optical sensors, yet its identity remains a mystery. From the Pacific coast to the Scottish Highlands, authentic images like these have been documented for decades. They've sparked questions about advanced technology, secret military programs, and, above all, the potential for life beyond Earth. Now, as well as video captured on Earth, a new generation of telescopes is gathering chemical signatures of distant worlds, data precise enough to suggest whether life might exist on planets over 120 light-years away.
We are already on the path to answering what is potentially one of humanity's oldest standing and grandest questions: are we alone?
We follow the trail from classified archives to the farthest reaches of space, examining what stands as the strongest evidence yet that we're not alone in this episode of Photo Evidence. It's one of the most scrutinized videos ever recorded. A small, white, wingless object, roughly the size of a jet fuselage, flying in ways no known aircraft can. Captured by US Navy pilots in 2004, the object, later nicknamed Tic Tac, appeared to descend rapidly from high altitude, hover over a visible disturbance in the ocean, and then accelerate away at astonishing speed. What made this encounter stand out was who recorded it: combat-trained Navy pilots and radar operators aboard the USS Princeton, one of the most advanced ships in the fleet. To this day, the Tic Tac remains unexplained, one of the clearest, most credible mysteries ever caught on camera. More than a decade later, in 2015, Navy pilots flying off the US East Coast captured this, known as gimbal. A disc-shaped object that appears to rotate against the winds as it moves. Again, it had no wings and no visible propulsion. Multiple sensors, including radar and infrared cameras, track the object, confirming its unusual movement. To this day, analysts can't fully explain how or why it appeared to rotate. That same year, another US Navy crew captured a second encounter off the coast of Florida, this one nicknamed Go Fast. A small white object appears to skim just above the ocean's surface, moving at speeds that seem impossible for any known aircraft. Infrared targeting cameras locked onto it, but radar returns were fragmentary. Once again, the key data, the altitude, trajectory, and velocity could not be confirmed. Together, these three encounters, Tic Tac, Gimbal, and Go Fast, represent the first time in history that the US Department of Defense publicly released footage of what it officially calls unidentified aerial phenomena. For investigators and the public alike, it was a watershed moment. The world's most powerful military had confirmed that there are objects in our skies behaving in ways we still can't explain. These were not amateur videos or internet fabrications. They were recorded by military sensors and confirmed by multiple observers. Long before the Tic Tac, Gimbal, and Go Fast, the US government and agencies around the world were documenting strange aerial phenomena. From grainy photographs labeled Flying Saucer in NASA archives to Air Force investigations under Project Blue Book, the Air Force's official program for investigating UFOs from 1947 to 1969, these sightings stretch back decades. A 2024 report emphasizes that unidentified often reflects insufficient data, not inauthenticity. As the report explains, insufficient data and information was compounded by inconsistent reporting and lack of continuity among investigations and investigative practices. Hundreds of entries span the National Archives catalogue, yet many arrive without radar logs, altitude data, or even reliable timestamps. Take, for example, a 1957 photograph from New Mexico, from Project Blue Book, or a case from Record Group 342, the Air Force's UFO investigation files, shows a UFO photographed in 1969. That's all the information available about it. The challenge isn't the photo itself, it's the missing context. Without it, an image can only raise questions. One striking example comes from Scotland in 1990, the Calvine photograph. Taken by a civilian witness, it shows a large, diamond-shaped object apparently suspended in the sky behind a military jet. For years it was classified, then released by the National Archives in 2009. Analysis by Sheffield Hallam University has confirmed the photo is authentic, printed on period-correct Kodak Ectacolor 78 paper. Established by its backstamp and supported by the abrasion tests you see here, which match the behavior of resin-coated color paper. There's no sign of digital or physical manipulation. Yet, crucial context is still missing. Precise location, exact date, and original negatives are gone. The result is a genuine photograph showing an unexplained subject, compelling evidence, but not proof. It shows how even authentic, unaltered images can leave us with questions science can't yet answer. Eyewitnesses have consistently described hovering lights, silent disks, and objects that appear to change direction instantaneously. But human perception is flawed. Brightness can deceive, distance can be misjudged, and speed can be exaggerated, even by trained pilots accustomed to high-speed flight and complex aerial maneuvers. From the 1940s through today, the same gaps and ambiguities appear again and again. In 2004, there was no official policy to retain data for encounters like the Tic Tac. Decades earlier, files from Project Blue Book often lacked consistent logs. Today, analysts are left piecing together fragments of incomplete historical records. In a bid for greater transparency, the US Department of Defense established the All-Domain Anomaly Resolution Office, AARO, in 2022. Its mission was to investigate reports of unidentified aerial phenomena and mitigate potential risks to safety and security. By October 2024, AARO have received over 1,650 reports. Many of these were ultimately explained: birds, drones, rocket launches, or even celestial objects. But more than half remain unresolved. Take case PR010, a 2022 sighting over Europe. Initially logged as a fast-moving metallic sphere, it sparked concern. However, after full analysis with multi-sensor data, including radar, optical, and satellite correlation, it was identified as a high-altitude balloon. This time, analysts had the context and complete data necessary to transform a mystery into a mundane explanation. If we go back to the Tic Tac for a moment, we can see the same thing. The video is very compelling, enough to convince high-ranking US service members. But experts have managed to cast just enough doubt over it to make people doubt its authenticity. To the human eye, the Tic Tac appears to accelerate, hover, and change direction impossibly fast. But appearances can be deceiving. One possible explanation is parallax, an optical illusion. When an observer moves, objects at different distances appear to shift relative to each other. Without knowing the range of the object, you cannot measure its speed. So the camera might be moving, and the target might be still. You've probably seen the same effect looking out the window of a moving train. Nearby objects blur past, distant mountains barely seem to move, and often, the only motion is your own. In 2004, the Navy kept no permanent radar logs for encounters like this. The data that could confirm what the pilots saw, the speed, altitude, trajectory, no longer exists. Once again, we're one piece of evidence short of making an airtight case. The United States is not unique in facing these uncertainties. Around the world, military and civilian observers have recorded images and radar tracks of unusual aerial objects, many unresolved for the same reasons: incomplete data, missing instrument readings, or a lack of corroborating sensors. In Brazil, Air Force radar logs from 1986 recorded multiple unidentified targets over São José dos Campos, tracked by both ground radar and pilots, but never confirmed. In Canada, NORAD monitoring stations have documented unexplained aerial intrusions over the Arctic, often linked later to balloons or sensor interference. And in the UK, the Ministry of Defence's declassified files contain hundreds of reports from the Cold War era. Bright lights, metallic objects, even photographs later attributed to aircraft or atmospheric phenomena. Military-grade sensors and trained observers across multiple nations consistently capture data that challenges conventional explanations. But what if, for the first time, we're beginning to collect enough data? New tools are now capturing these phenomena in unprecedented detail. Coordinated observations, advanced analytics, and multiple detection systems mean that what once existed only as fleeting, unexplained blips can now be studied systematically.
I'm Niku Madhusudan. I'm a professor of astrophysics and exoplanetary science at the Institute of Astronomy at the University of Cambridge. My expertise is in working on exoplanetary atmospheres, trying to understand what the atmospheric compositions of these exoplanets are. By exoplanets, I mean planets orbiting stars outside our solar system. And for the first time, we are trying to understand what the atmospheric compositions of potentially habitable planets are like. But what if we finally start to have enough data to investigate the possibility of habitability and potentially life elsewhere? Today, we have the James Webb Space Telescope, the largest telescope in space humanity has ever built. See, for thousands of years, we have a species have always looked at the sky, made stories about it, looked at the heavenly objects, tried to understand what they're made of, what they're about. But did you know, until just about 100 years ago, we didn't know what the sun was made of, let alone the planets, let alone the cosmos as a whole. And just about 30 years ago, we did not know of any planet outside the solar system. And today, for the first time in the history of our species, we are beginning to not only measure atmospheric properties of planets around other stars, but actually trying to understand their chemical compositions and see if any of these planets could support habitable conditions and indeed life on them. And that is being made possible by the James Webb Space Telescope today. So our humble beginnings in exoplanetary science starts with planets that have no analogs in the solar system. So the first planet that was discovered around another star outside the solar system was 51 Peg-b. Now this planet is what is known as a hot Jupiter. So let's take the architecture of the solar system. So the Earth is at a distance of 1 astronomical unit. Jupiter, which is 10 times larger than the Earth, is at a distance of 5 astronomical units. Now on the other side, Mercury is at a distance of about 0.4 AU. This planet, 51 Peg-b, which is a typical hot Jupiter, it is situated at a distance that is 10 times closer to the Sun than our own innermost planet Mercury is to the Sun. So it is situated within about 0.05 AU. Now you have to imagine this is the first exoplanet that we had ever discovered around a Sun-like star. It took another 5 years in the year 2000 when the first transiting planets were discovered. And what this does is it allows one to measure the radius of the planet as the planet is transiting in front of the star, is going in front of the star, in other words, an eclipse. And because of that, we have been able to measure the radii of these planets and confirm that these are indeed Jupiter-sized, Jupiter-mass planets orbiting very close to their stars. So today, we know that these hot Jupiters are real, and we could confirm that that was indeed the first discovery of a planet around a Sun-like star. But what have we learned in the 30 years since the first discovery? Today, we know of over 6,000 exoplanets out there. Now these planets are extremely diverse. They come in all kinds of sizes, they come in all kinds of masses and orbital architectures and the kinds of stars they orbit. The diversity of planets we see out there far surpasses the planetary diversity we see in the solar system. We know thousands of such planets, yet we have no planet of that size in the solar system. What could these planets be like? What are their atmospheres like? What are their interiors like? Can they be habitable? These are all some of the burning big open questions at the forefront of the field that we are trying to uncover right now. So of these thousands of exoplanets orbiting stars of different kinds, there is one that stands out, and that is K2-18b. This is the planet for which the first measurements have been made of carbon-bearing molecules in its atmosphere, and this is at the forefront in the search for life on exoplanets. But before we get into the details of the planet, let's see what is it that makes this planet so special and why is it that we are talking about these observations now. So until 5 years ago, our best telescope in space to look at atmospheres of exoplanets was the Hubble Space Telescope. But just in the last few years, this field of exoplanet atmospheres is being revolutionized by a new telescope, that's the James Webb Space Telescope. So JWST is a transformational development in our ability to observe planetary atmospheres, especially exoplanetary atmospheres. There are two reasons for that. First, its sheer size. With the Hubble Space Telescope, the diameter of the telescope is 2.4 meters to be precise. With the James Webb Space Telescope, this is the largest space telescope humanity has ever built, with a diameter that is about 6.5 meters. So that is more than 2.5 times larger than the Hubble Space Telescope, which means the collecting area is more than 6 times larger. The Hubble Space Telescope is mostly an optical telescope, but it also has infrared capability, but only until about 1.8 micron. Whereas the James Webb Space Telescope is primarily an infrared telescope, and it goes all the way to mid-infrared wavelengths, slightly even above 20 micron. So now we have this entire wavelength range for JWST all the way from about 0.8 micron to 20 plus micron. We have now measured spectra of a number of planets with the James Webb Space Telescope just in the last few years. Many of them are giant planets like the hot Jupiters we talked about, but we are also going down to smaller and cooler planets. And for the first time ever, we have the sensitivity to look at the atmospheric composition of planets that are in the habitable zones of their host stars. Whereas in exoplanets, we have this entire range in between, which we call as sub-Neptunes. These are planets that are in between Neptune and Earth in size and mass, is it possible that planets can be significantly bigger than Earth and still be habitable? K2-18b is what is known as a temperate sub-Neptune. This is a planet that is roughly 2.5 times the size of Earth and roughly 9 times the mass of Earth. But most importantly, the planet sits what is known as in the habitable zone of its host star. The total radiation it receives from its host star is very similar to what the Earth receives from the Sun. You can calculate an average temperature of the planet just based on its distance to the star. This is known as the equilibrium temperature, and it comes to about 300 Kelvin. Now we have to be clear that there are several habitable exoplanets known right now, dozens, but not all of them are conducive for atmospheric observations. Some are too far to get good sensitivity on the atmospheric observations. Some are too small to be able to detect their atmospheres any robustly. But K2-18b is just that one planet where we have been able to make atmospheric observations for the first time ever for a habitable zone planet. Let's look at what those observations look like. Several teams had measured the atmospheric spectrum of K2-18b with the Hubble Space Telescope, and you see this is all we could see. You note that the maximum wavelength it went to is about 1.7, 1.8 micron, and there was only one blip of a spectral feature that was visible at the time. What is this feature due to? Some claimed it was water vapor. Some others claimed it was due to methane. But because there was just that one feature, it wasn't clear what exactly in the atmosphere is causing that spectral feature. Now in 2023, the first observations were made with the James Webb Space Telescope of the same planet. As you can see, this wavelength range is going between 1 and 5 micron. If you were to see which part of this wavelength range was covered by Hubble, it was just that. Where these observations was made with 8 transits of the planet in front of the star, this was just with 1 transit each, so 1 plus 1. So 1 transit in this wavelength range and another transit in this wavelength range, both with JWST. So in 14 hours of JWST time, we get the spectacular spectrum. This first detection allowed us to make the first detections of carbon-bearing molecules in the atmosphere of a habitable zone planet. We have detected methane and we have detected carbon dioxide. What we also saw was a very, very tentative hint of a third molecule. Now this molecule was dimethyl sulfide. Dimethyl sulfide was predicted to be a biomarker on exoplanets, including Haitian worlds, for the longest time. So for 20 years, this molecule has been predicted as a good biomarker to look for in other planets, in other atmospheres. Why? Because on Earth, it is predominantly produced by life, mostly by microorganisms in the Earth's oceans. So if we are seeing it in a planet like K2-18b, there is a possible evidence of biological activity on the planet. So our initial observations of K2-18b in the near infrared, which is what this 1 to 5 micron range was, told us that the atmosphere is a hydrogen-rich atmosphere with high abundances of methane and carbon dioxide in the atmosphere. What we didn't detect were ammonia and carbon monoxide, in other words, a Haitian world. Haitian world means a hydrogen-rich atmosphere and an ocean-covered surface, and this was predicted for K2-18b. We have only very tentative evidence for DMS in these observations, but we need more observations to see if that is indeed present. In April 2025, we announced the first mid-infrared spectrum of K2-18b. This is the first spectrum ever obtained of a habitable zone exoplanet in the mid-infrared. So this spectrum shows several features which could be due to dimethyl sulfide or dimethyl disulfide, which is a sister molecule, very much like DMS, has similar spectral feature, or both. So how confident are we? The confidence is usually measured by how much a model including DMS is favored over a model that does not include DMS. So here we have 2 spectra obtained with JWST. This is the near infrared and this is the mid infrared. In both these wavelength ranges, we are seeing tentative evidence for this one molecule, which is DMS. And in this case, the maximum in the near infrared we have is 2.4 sigma, and the maximum in the mid infrared that we have is 3.4 sigma. A model including DMS is favored at about at least 95% confidence over a model that doesn't have DMS. In other words, a model with DMS is favored at a 20-to-1 odds at least over a model that does not have DMS. And this is one case for a hot Jupiter WST-39b. And you see that the spectrum is also obtained in the same wavelength range with the same instrument, 5 to 12 micron, same as K2-18b. In all these cases, be it for K2-18b, a potential Haitian world, or hot Jupiters, there's JWST 39b, JWST 17b, the story is the same. These are the first observations being made in the infrared. These are very tentative indications of molecules in that wavelength range. So these are the first observations we are making of these kinds of planets, and there are many unknowns. So we have to be cautious in how we are actually interpreting these observations. Is this signal of DMS authentic? Because if I were to draw a flat line across this spectrum, you would see that several of these points touch that flat line. As you can see, while most of these points pass through this flat line, there are points out there that are not normally distributed or randomly distributed across that flat line. The other angle is to ask if the signal is uniquely identified. One study argues that the signal could be from a few other molecules that can also explain the data that we are seeing in the medium. Many of those molecules are not known to be produced naturally. So several of those molecules are produced by human activities on Earth. However, there is at least one molecule which can in principle be produced by atmospheric chemistry. So there are various efforts underway to see if there are other molecules like that could also explain this feature. What we know is that the atmosphere definitely has a substantial amount of methane and carbon dioxide at about 1% each. In a hydrogen-rich atmosphere in the background, the atmosphere does not have ammonia and carbon monoxide. So to me, this is the biggest breakthrough that is happening in exoplanetary science, is our ability to look at atmospheres of habitable zone planets and have the capability to even detect biomarkers, and being able to debate whether they are not actually biomarkers is a big breakthrough in the field and a big transformational change in our search for life. We are already on the path to answering what is potentially one of humanity's oldest standing and grandest questions: are we alone? We have the James Webb Space Telescope, we have the targets, and we have the telescope that can look at those targets and detect those atmospheric signatures, as we've already demonstrated with our observations. So more observations, more deeper, can get us one step closer to knowing whether these are the molecules that are actually causing the absorption that we are seeing, the spectra that we are seeing, and if there is actually any evidence for life and habitable conditions on this planet. At the end of the decade, there are also large facilities, telescopes coming up on ground. So this is the extremely large telescope is going to be a 39-meter telescope in Chile by the European Southern Observatory, which is going to be the largest telescope on ground ever built. This decade, indeed, I think would be serving as the launch pad in the search for life. But whether we will actually have that conclusive evidence for life in the next few years or the next decade or in a few decades, we will have to just wait and see. What we do know is that we have the capability to find life elsewhere if it is actually out there. So why is K2-18b special, and why is this moment special? It's because the story of K2-18b is showing us that the number of habitable environments out there could be much more than just looking for Earth-like planets. And these are planets with hydrogen-rich atmospheres, ocean-covered surfaces, which can have habitable conditions in the oceans and can be much larger than Earth-like planets. So is there life out there? We don't know yet, but we could be hopeful because the galaxy is full of planets and there could be lots of habitable planets out there. Have we detected life on K2-18b? The answer is clearly no. We have tentative evidence for this molecule DMS, but we don't have conclusive evidence yet. We are still at a 2-3 sigma level, which is tentative, because these sorts of environments like Heisenberg's have no analogs in the solar system. So if their life exists on those planets, and if there are spectral features we are seeing, are we actually well equipped to interpret those signals as uniquely due to life? And that, I think, is the big question. Are we prepared to find life as we don't know it?